A very good evening, class 11th. Moving on with the group 14 of the P block chapter of class 11th. We'll be doing a quick class on this group as a summary class. Hope you are doing all well, staying happy, healthy and safe. Let's begin with the members of group 14. The members are carbon, silicon, germanium, tin and lead. The mnemonics wise, this group can easily be learnt by class से गए snookers pub. Class से गए snookers pub can be a way of learning it up. Now moving to the atomic number. Each one of you definitely knows that carbon has an atomic number of 6. After this, if you know the order, there is no need to learn the atomic number. You go from here to here, just add 8. You go from here to here, add 18. Again go from the next member, again add 18. And finally you add 32. These are known as the magic numbers to come to the next member of each and every group. Fine. Moving on to the electronic configuration. So for 6, your configuration is 1s2, 2s2, 2p2. For 14, the electronic configuration would be 1s2, 2s2, 2p6, 3s2, 3p2. For germanium, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 gets incorporated here and a 4p2. Similarly, when we talk about tin, the configuration of the outermost shell would be 5s2, 4d10 and a 5p2. Moving on to the last member, lead, the configuration would be a 6s2. Now you have a 4f14, then a 5d10 followed by a 6p2. So in all of them, your last p subshell has 2 electrons and last s subshell is fully filled. So when we talk about the general configuration is NS2, NP2 for group number 14. General variations as you move down the group. As I move down the group, as you can see, a shell is being added. Generally speaking, the size always increases on moving down the group. Now what about ionization energy? Ionization energy is inversely proportional to size. So if the size is increasing, your ionization energy down the group always decreases. This is the amount of energy required to remove the most loosely bound electron from an atom. So since the size is increasing, the outermost electron moves away, so it's easier to remove. So the energy required is less. Moving on to metallic character. Metallic character is related to your ionization energy. So if your ionization energy is high, so your metallic character becomes low. So it is inversely related to ionization energy. Hence, metallic character on moving down the group always increases, while the ionization energy goes on decreasing. Since we are on the P block and I need to compare group 13 versus group 14. When I talk about group 13, the configuration is NS2NP1, and when you talk about group 14, the general configuration is NS2NP2. So nothing grand is happening in the Nothing grand is happening in the configuration. No stability, no half filled, or nothing stabilizes the electronic configuration. So as you move from group 13 member to 14 member, the size decreases. Since the size decreases, when we talk about ionization energy, then group 14 member has a higher ionization energy than the group 13 because members of 14 are smaller in size. Similarly, when we talk about electron gain enthalpy, then again 14 would have more easily electron gain than 13th group. That is again due to the lower size of group number 14 members. Moving on to the specific properties. I did the general properties. Now for these members of group number 14, when I talk about size, I expect carbon to be the smallest, followed by silicon. Now after silicon you have germanium, but there is a size similarity owing to the presence of 3d10. Again, when you move from germanium to tin, the size again increases, but when you move from tin to lead, again the size there is a similarity. Now this is incorporated to the 3D10 and this is incorporated to the 4F14. Now presence of D and F subshell always causes having a poor shielding effect of D and F. This causes a increase in effective nuclear charge. So if the effective nuclear charge increases, automatically the size does not lead to a size does not increase much even if while you are moving down the group. So as you move down the group, size to badhna chahiye because shells are increasing. But because of the D and F incorporated, whenever you have D and F incorporated, due to their poor shielding effect, they are unable to cover up the nucleus. So the attraction of the nucleus to the last electron increases. Hence the size does not increase much. Moving to the ionization energy. Now ionization energy is highest for carbon owing to its small size, and then you have it for silicon. Now since their sizes are similar, their ionization also energies are similar, again owing to the 3D10. Then you have again tin below this, but surprise factor is with this point. This is the area. Why does lead have a higher ionization energy is again due to the 4F14 electrons which have a poor shielding effect. Therefore, effective nuclear charge increases. Therefore, removal of electron needs larger energy. The removal of electron will require a larger energy. Therefore, there is a surprise factor here, which is, I remind again, owing to the 4F14 being present in lead. Moving down to the metallic character. Now, when you talk about the metallic character always increases down the group. So, with respect to carbon, the metallic character would increase, then germanium, then tin, and then lead. Carbon is a non-metal. Silicon is also a non-metal, while germanium is a metalloid. While these two come under the category of metals. Is that fine? Let's talk about the oxidation states of group number 14. The general configuration as done is Ns2Np2. So your electrons in the box configuration would be like this, this and this. Now under the excited state, this electron can shift here. Therefore, you would have Ns1 and Np would have 3. Now owing to this shift of electron, this is the reason that 4 electrons can form bonds. So the oxidation states either are only if P is used, it is +2. If both S and P are used, then it is +4. Now in this case, what happens is we observe that as you move down the group, due to the point of inert pair effect, on moving down the group, +2 is more common down the group. In fact, when we talk about lead would only show +2 much more as compared to +4, which is the reason we say lead shows inert pair effect. Inert pair effect is actually a property of the last member of each and every group. I'll just give a quick recap. When we talk about lead, in case of lead, if you remember, the configuration of lead was 6s2, 4f14, 5d10 and a 6p2, and here you have the nuclear charge. Due to the incorporation of 4f, D and F subshells in the last member, they show a poor shielding effect. That is, they do not cover up the nucleus well. Hence, the nuclear charge increases. Secondly, S subshell has a high penetration power. Means it is found closer to the nucleus. So these electrons are held tightly by the nucleus. Whereas comparatively, the 6p electrons are not held tightly. owing to the presence of these two. So because of these two, since the nuclear charge increases, 6s is held much more tightly, hence only p electrons of the outermost shell participate in bonding. Therefore, the oxidation state decreases by 2 in the last member. Hence, the reluctance of the s electrons to participate in bonding is the way we define inert pair effect. So, inert pair effect once again is the reluctance of the s electrons of the last member of each group to participate in bonding owing to its penetration power and being held tightly by the nucleus, while the other members do show a +2 as well as a +4. So, if you are asked in which case for +2 oxidation state, it is found that the configuration according to the EC of these elements, it is found that as compared to germanium, tin would show a better 2 oxidation state and best would be shown by your lead. This is the gist of inert pair effect. Always the lower by 2 oxidation state becomes more predominant as you move down the group. Fine. Moving on to the anomalous properties of carbon. The first member of every group has anomalous properties. So when we talk about carbon, the first important property is that it has only s and the p subshell. Therefore, there are only 4 orbitals in the outermost shell. Hence, there is also an absence of the d subshell. Therefore, maximum covalency is equal to 4. Carbon can never form compounds beyond 4. That is, it can only form 4 bonds. Hence, no such compounds where there are more than 4 bonds are observed in case of carbon. For example, when I talk about compounds like SiF6 2- or germanium F6 2-, they do exist because they have a d orbital. But a similar compound, if I say CF6 2-, then nothing of this sort is possible because the maximum covalency of carbon can only be 4 due to the absence of d subshell, while the other members can show 6 bonds in them owing to the presence of the d subshell. Is that fine? Moving on to the next. Carbon also has a property of strong double bonds. Now, why is that? That is, we also call it as a p-pi bonding is shown by carbon. Why does carbon show a p-pi bonding? Due to its small size, your pi bond is effective because overlap of orbitals is effective, and this can easily be observed. We very well know of such compounds in ketones. We know of the cyanide. We know of the carbon monoxide. So these are also alkenes, alkynes. So these are some compounds where we very well know that carbon does have tendency to show multiple bond formation is a property special to carbon. Moving on to the next important property, which is catenation. What is catenation? This is your self-combining capacity, which is owing to the strong carbon-carbon bond. The reason is due to the small size of carbon, this overlap is effective and these electron pairs are held tightly by both the nuclei. Hence, this leads to long chains, branches and ringed compounds of carbon. When we talk about catenation, it is found that carbon shows maximum catenation in this group, followed by silicon, which has much lesser catenation. Again, this is more than germanium. Rest of them do not show any catenation, and we don't talk about catenation for larger members because their bonds are weak. Carbon is the one which shows maximum catenation of all the elements in the periodic table. That is the reason the base of organic chemistry, where you have compounds of alkanes, alkenes, alkynes, all long series are possible due to the catenation property of carbon. And the reason is the strong carbon-carbon bond. Let's now talk about the oxides of carbon. The first oxide of carbon is carbon monoxide. You very well know, in case of carbon monoxide, you have a coordinate bond between oxygen and carbon, and there are one lone pair on each of the carbon and oxygen. There's a triple bond here. Now this is a neutral oxide. That's point number one. Secondly, this particular carbon monoxide is also known as a slow poison. Now why is it called as slow poison? Now each one of us has got blood which combines with oxygen, where the hemoglobin of the blood binds to the oxygen, and you are alive due to this breathing where hemoglobin binds to oxygen. Now in the presence of carbon monoxide, it is found that hemoglobin combines with carbon monoxide to an extent of 300 times more. So in the presence of carbon monoxide, your hemoglobin gets blocked. This is again a very strong bond. Hence, your hemoglobin is not free to bind with oxygen, and the person suffocates to death whenever he is in an atmosphere of carbon monoxide for a prolonged period. Other than this, carbon monoxide has got uses. As far as the uses are concerned, the uses are, if you have a mixture of hydrogen gas and carbon monoxide gas in the ratio of 1:1, this is called as water gas. That's the name. While if you have your carbon monoxide gas is to nitrogen gas in the ratio of 1:2, this is known as producer gas, and it is used in industrial processes. So carbon monoxide has uses in industrial processes with hydrogen in 1:1 and with nitrogen in 1:2. That is the use of carbon monoxide. Moving on to the second oxide of carbon, which is carbon dioxide. This is an acidic oxide. Point number one. In this case, carbon has an oxidation state of +4. How do you know it is acidic? Because carbon dioxide dissolves in water to form carbonic acid, which is of course a weak acid, but does dissociate you to give it H positive and carbonate ion. So you do show a presence of H positive by the litmus, or all your cold drinks are acidic owing to the presence of carbon dioxide in them. Other than this, it is also dry ice, because if you have carbon dioxide gas, you decrease the temperature and increase the pressure. This gets solidified, and this solidified carbon dioxide is called as dry ice. Beyond this, the other important use of this particular carbon dioxide is, carbon dioxide has a structure like this, where it has 2 sigma bonds and 2 pi bonds. So the hybridization is sp, the bond angle is 180, the shape is linear according to VSEPR theory. Also, this gas is non-supporter of combustion and it is heavy, so it is used in fire extinguishing. Also is a greenhouse gas, that is, it is causing the temperature of the Earth's atmosphere to increase. Owing to the presence of carbon dioxide around the Earth does not let the heat of the sun move out of its atmosphere, so our temperature is continuously increasing due to this carbon dioxide in the atmosphere. Moving on to the allotropes of carbon. Under the allotropes of carbon, the first allotrope is diamond, where you have a carbon bonded to 4 carbons, again which is bonded to 4 carbons, and so on. This is an open structure which continues, where each carbon has got 4 bonds, so the hybridization is sp3, the bond angle is 109.5. This is a very hard substance and has a very high refractive index, so it shows multiple reflections, hence is shiny. Also beyond this, the second allotrope is graphite. How is graphite different? In case of graphite, the structure is like this. It has a layered structure like this, followed by another layer at the other end. So because of these layered structures, each carbon only has 3 bonds. And since it has only 3 bonds, there is 1 electron free between the layers, and this free electron makes it conducting. And there is a presence of van der Waals force of attraction between the layers. Of course, these bonds are also free at the ends. At the ends, you again have free bonds, which makes it again reactive. So is true here. For diamond also, the ends are not sealed. There are free bonds here where something can bind, so they are reactive. Similarly, carbon also has got free bonds at the end, so it becomes reactive. The last and the latest allotrope is fullerene, which is also called as the Buckminster fullerene. Now this is a football-like structure which is closed and there are no dangling bonds. Since there are no dangling bonds, this is the purest form of carbon. At room temperature, we have graphite. This is the allotrope which has got delta HF not to be 0. That is, heat of formation of graphite is taken to be 0 because carbon does exist as diamond, graphite and fullerene. But diamond and fullerene exist under special conditions, while graphite is found at room temperature and abundantly available. So when we talk about heat of formation under the elemental state, it is most thermodynamically stable and exists at room temperature, so we take its enthalpy of formation to be 0, while for these two the enthalpy of formation cannot be taken to be 0. Is that fine? I would now be doing some important topics. The first is hydrolysis of CCl4 in comparison to SiCl4. Both of them have got tetrahedral geometry, and the hydrolysis means reaction with water. For silicon also, it has a tetrahedral geometry and there is reaction with water. The lone pair of water, oxygen that is, goes and attacks onto silicon in the presence of the vacant d orbital, whereas a lone pair here cannot attack it because carbon has no vacant d orbitals for the lone pair to form a coordinate bond. This leads to an intermediate structure which looks like this. Silicon does form 5 bonds as an intermediate, while carbon can never form 5 bonds owing to its limitation of absence of d orbital. This then loses HCl to form a compound with 3 chlorines and 1 OH. This reaction will continue with 3 water molecules and finally you would end up in silicon tetrahydroxide. So hydrolysis is a property of SiCl4 due to presence of d orbitals, whereas CCl4 does not react with water, it leads to immiscible layers. They don't mix into each other. There are immiscible layers if you mix water and CCl4. The reason is water does not react with CCl4 because there is absence of d orbital where the water can coordinate, while this can do so due to the presence of d orbitals. The next question is, out of these two, which exists and which does not? And the answer is, this exists, this does not. The reason is, that large size of Cl, so 6 Cls cannot be accommodated around the silicon atom, while 6 fluorines, F being small, can easily be accommodated with silicon. Also, Si to F bond is strong and stable as compared to silicon to chlorine bond. Because of their larger size, the covalent bond is not that effective, while Si to Cl bond is weaker. So, 6 chlorines cause steric hindrance around silicon. They cannot adjust around silicon because of their large size, while 6 fluorines can easily accommodate or form bonds around silicon. The next question is, lead tetraiodide does not exist, and the answer is Pb is the last member, shows inert pair effect. Therefore, the common oxidation state is going to be +2. Therefore, in this compound of PbI4, you can see it has a +4 oxidation state. That is why it does not exist. But to speak of PbF4, despite the fact that lead here has +4, but this compound exists. The reason is the strong PbF bond leads to this formation. Also, it has a ionic character because F is the most electronegative atom. So, this atom is able to pull electrons from lead, while normally iodine is not able to pull electrons from lead. So, inert pair effect becomes predominant, while PbF4 does exist as an ionic compound owing to the high electronegativity of fluorine. So, it can cause Pb to go to a +4 oxidation state. Fine. How is CO2 and SiO2 structurally different? They have to be. CO2 is a gas while SiO2 is a solid. Why so? In case of CO2, the structure ends here. It is single units, exists as discrete molecules. Therefore, intermolecular force of attraction is weak, which of course is London force. When we talk about SiO2, SiO2 cannot form this. Why? Because silicon does not form p-pi multiple bonding. So, this is not possible. Hence, what does this structure look like? Each silicon is bonded to 4 oxygens like this, and each oxygen is bonded to 1 silicon like this, 2 silicons like this, owing to its valency. So, it forms a large cage-like structure where you can see there are 1, 2, 3, 4, 5, 6, 7 and 8. 8-membered rings formed such a large structure. It becomes a covalent solid. It has a network structure. The intermolecular force of attraction becomes high. Therefore, due to this large giant structure, it exists as a solid. Because this does not stop, it continues. Fine. So, that is the reason why SiO2 is a solid while CO2 is a gas. The next question is, you have to choose the more stable compound out of each of the following pairs. When we talk about germanium, germanium is showing a +4 oxidation state here and a +2 here, and it can definitely show a +4. So, this is more stable because it is in the middle of the group. It does not belong to the last member to show inert pair effect. Coming to the lead. Now, lead is the last member. Since it's the last member, it would show inert pair effect. Because of inert pair effect, the common oxidation state would be +2 and not +4. Why is that? As I already explained, the S electrons do not participate in bonding. So, in the configuration you have NS2, NP2. This does not participate, only this participates. And why does this not participate? Because it is held tightly by the nucleus. Why so? Due to the presence of the 4f and the 5d electrons, which cause the effective nuclear charge to increase. Hence, the s electrons are held tightly. So, out of these two, the more stable compound would be +2 oxidation state. Coming to these two, this shows lead is in the oxidation state of +2. This shows lead is in the oxidation state of +4. So, we very well know due to inert pair effect, this is the compound which would be more stable. Another such question related to these two is, PbO2 is considered as a very strong oxidizing agent, and the reason for it is that PbO2 prefers to go to PbO. The reason is inert pair effect. So, your lead goes from +4 to +2. There is a decrease in oxidation number, therefore prefers reduction, hence is a good oxidizing agent because lead is stable in +2 oxidation state, being the last member. Moving to the next question, which out of PbCl2 and PbCl4 is more covalent? And the answer lies in the Fajan's rules. According to Fajan's rule, the covalent character depends on the metal. The covalent character is found to increase if the metal is small in size, there is more positive charge on the metal, and the metal is from the D block of elements. Now, in these two cases, lead has got a +2 charge here, whereas it has a +4 charge here. So, as just said, more positive charge shows a greater covalent character. Due to more positive charge, it would show a covalent character. It would have a higher polarizing power, will pull the electron cloud of chlorine towards itself. Hence, the covalent character would increase due to the positive charge on lead, which will pull the electron clouds back towards itself from chlorine, causing more polarizability and more covalent character. In case you are struggling with Fajan's rule, please watch my video on Fajan's rules. You can type Seema Makhijani Fajan's rules by Seema Makhijani on YouTube and you can reach that particular video fast. Moving ahead. Carbon compounds are considered to be electron precise. Now, what do we mean by this? For example, you have a compound of carbon which is, let's say, a hydride, that is methane. So, when we talk about methane, all 4 electrons of carbons have been used up. There is no lone pair, so it is not electron rich. Octet complete, so it is not electron deficient. So, neither does it have extra electrons, nor does it have running short of electron. So, it is neither a Lewis acid nor a Lewis base. What is a Lewis acid? Lewis acid is electron acceptor and Lewis base is electron